Hello, my name's David Finlayson with Chesapeake Technology, and today I'd like to show off some of the features of our new second generation gritter. Probably the most anticipated new feature of the gritter is support for cube gridding algorithm. Many hydrographic offices are requiring cube surfaces as deliverables, and now it's possible to use SonarWiz to create them. The cube is also really useful for geophysical surveys as well, since it tends to produce the best bathymetric surfaces even when the sonar data isn't optimal, which is often the case when bathymetry collection requirements need to be balanced against other mission objectives. To create a cube surface in SonarWiz, you have to first calculate the positional uncertainty of each of the soundings in the dataset. In the latest version of SonarWiz, this is done during the merge step. We've added an error model page to our merge wizard that allows you to pick an appropriate error model for your survey. So for this demonstration, we're going to select these four files here, right-click, and merge. We'll step through the regular merge process and get straight to the error model page. This is what's new. We currently support three different error models: the sonar provided model, the simple IHO model, and the full error model. In the sonar provided model, some modern sonars are calculating their own uncertainty values dynamically during acquisition. If your sonar has this capability, you can select this option to pass those uncertainty estimates onto the gritter. The second model is the simple IHO model. This option assumes that the positional error in your soundings meets the standard of the selected IHO survey order, but just barely. This is a good option for non-hydrographic surveys that are primarily interested in Q as a robust gridding algorithm and don't need or care about the sounding uncertainty calculations. Finally, we've got the full error model. The full error model calculates the uncertainty of each sounding using a detailed propagated uncertainty formula, which accounts for the actual position and measurement precision of each instrument on your platform. This is the model to use if you require sounding uncertainty estimates as a deliverable. You can see in this screen that I filled out the measurement values for the port and starboard channel of the interferometer, along with estimates of the various measurement uncertainties, and there are quite a few of them. So we'll click Next and Finish and apply those calculations to all the soundings in this small data set. Okay, so that's done. Now what we're going to do is grid these four lines. So what we do is make sure that the four lines that you want, or make sure that all the lines that you want to grid are checked on here, and arrange the screen about where you want the grid to be. Then we select Grids, right-click, and Create New Grid. Here's the new dialog. The upper section up here shows the grid bounds. And you can either go, by default it opens up and it shows the grid bounds of the screen here. But if you want to do a tighter grid, you can click on this little button here and make the grid a little bit more centered on the data. The grid bounds will always snap to an even multiple of the cell size. We have a 1/2 meter cell size here, and you can see that it nicely rounded the numbers so that we'll have an even number of cells in there, no weird floating point numbers. The next thing we do is we select our primary grid surface, and this is going to be a depth surface. And we have four algorithms for calculating depth: trim to mean, median, cube, and inverse distance weighted. We're going to use cube. And then you'll notice that there are some auxiliary grid outputs that can be created at the same time the depth grid is made. You can do basic univariate statistics like the count or minimum and maximum values in each node, standard deviations. You can also calculate some unique ones that are special to cube processing. We have an uncertainty grid, the hypothesis count, and the hypothesis strength. For this one, we'll just create an uncertainty grid and the cube grid. Now we click OK, and it doesn't take too long to generate this grid. All right, there we go. Now I'm going to turn off the raw Bathy lines and let the uncertainty grid show through. So if we click the color legend here and go to standard deviations, we can change the scale of the uncertainty grid. So here, change it from, say, 0 to 2 meters. And interferometric data has a low precision sometimes, and you can tell with the uncertainty grid how good it did. Uncheck this one, and now we can look at the depth grid, and there's the shaded relief of the depth, and it looks really good. Another thing we can do with the cube gritter, the new gritter, is look at amplitude data. We've put quite a bit of interesting stuff in there as well. So if we switch the drawing mode from bathymetry to backscatter, now let's change this to backscatter and scale to loaded data. So there is the raw backscatter from our data set here. There's still a little bit of a cross-track artifact. This is the raw data, so let's process that a little bit. We'll use the process backscatter button here. Check all. You can usually just go with the defaults here. I'm going to turn this down so it runs a little faster. So right now it's going to normalize all the backscatter in the entire data set. And the resulting values are not in decibels anymore, they're in normalized values. So we'll need to readjust the color bar. So 100% would be average. Anything less than 100% would be less than average amplitude, and above 100% is above average amplitude. This value looks like it was already set. From 90% to 115% gives us a pretty nice raw backscatter look here. What we want to do is grid this. So again, we'll click on the grid here, and we'll create a new grid. This time we'll select amplitude, half meter cell size, and we've got 4 new options. We have a mean amplitude, median amplitude grid, blended, and nearest range. I think the blend and nearest range are interesting. So let's start with blend. And we don't need any optional grids here. We'll create one of those. And then we'll do it again and create a nearest. That way we can compare the two. All right, those are now added. So let's turn off the raw bathymetry again so we can see the grids. Now, these two, the nearest algorithm and the blended algorithm, are designed for different purposes. When you're trying to find targets, you want to preserve as much of the texture and fine detail of each grid as possible. So what nearest does is it guarantees that every node in the cell will only come from one track line. There won't be any overlapping or any averaging together. But it picks the one that's closest to nadir. So here we can see there's 3 nadir stripes, and in between there's a seam between the 2 track lines above and below. But it always shows pretty much the best possible presentation of the data. There's no smoothing or blurring or anything. This is ideal if what you're doing is target detection, but it's probably less than ideal if what you want to do is habitat characterization. For that, you'd want the blended algorithm. So here's the blended version. So again, I'll turn that off. There's the nearest, and you can see the 3 track line artifacts. There's actually 4 in there. Now we turn blend on, and they're gone. What the blended algorithm is designed to do is seamlessly transition from one track line to the next. It takes advantage of the overlap between 2 neighboring lines to smoothly feather them into each other. And if there's enough overlap, that transition is nearly seamless, like it is here. The downside to this algorithm is it tends to make fine targets a little bit blurrier, especially if they don't present well on both sides, in both track lines, or if you have 4 or 5 overlapping together. So again, if you're doing habitat style work and you want a seamless mosaic, use the blend algorithm. If you want target detection and you really care about picking out individual targets on the seafloor, you can use the nearest amplitude.